Thank you, Peter. Yeah, so I would like to, in this talk, I would like to give a little bit of insight into the data generation for perception tasks in autonomous driving context. I will introduce two of our works which we published recently. And yeah, so I just want to make a remark that everything I'm talking about is it's all focused on deep learning based computer vision tasks, and actually only in the context of autonomous driving. So don't be surprised if I'm using only the automotive data in the works. Yeah. So I'll start with a short introduction why neural networks in AD might need generated data. Then I will give a little bit of the overview of our methods, what are we doing in this context. And maybe at the end, we all even have some time for a short demo on data generation. First, I would like to show this paper from probably the first NIPS conference, which dates back to 1988. So almost 30 years ago, more than that, where the author of the paper deployed a road image generator for training the neural network used for navigating the autonomous vehicle called Alvin. So on the slide, you can see the real road image used back then and a simulated image, which has been used for training neural networks in this autonomous vehicle more than 30 years ago. So simulation and self-driving has a long history already, I would say. And why is that? So the main advantage of generated training data, which has been used for training neural networks, is that we potentially has no bound on number and variance of traffic scenarios, which can be used. And the more data we know, the better. So this plot gives a rough understanding of this principle. It shows experimental results for the detection model, which has been trained on different fractions of data. So here, three colors depict detection performance of a deep learning model on three different data sets. So various glyphs depict sizes of training data. Triangle corresponds to 2.5% of original data size, and the star corresponds to the full data set. So for all experiments, it's quite evident that increasing the size of training data improves performance a lot. And so data variance matters. Another advantage of having generated simulated data at hand is the annotation cost. So in this paper from Sebastian Richter, I guess, so they report that semantic segmentation rendering allowed to speed up annotation by a factor of 1,000. So it's especially important for such tasks as semantic segmentation, where you literally, which is also called pixel dense segmentation, where you literally need to annotate every single pixel in the image, which might be 1,000 by 500 or 2,000 by 1,000 pixels. So it's more than 1 million of pixels. So generated data is inevitable when it comes to a long tail of rare events. For example, the one which you can see on this GIF video. And it's also important in a use case where we face near accident scenario. So there's always the non-tech people challenge engineers with this infamous trolley problem question. So if a autonomous vehicle would have a choice who to run over, and so it's a rather philosophical question, but if it comes to a real world scenarios, the real data acquisition is impossible when it comes to near accident scenarios. So we just cannot put somebody in danger in order to capture our data set and annotate it. So this is where the simulated data comes really in handy. So here's, for example, a screenshot of last year Scaled ML conference and a screenshot of a Andrei Karpathy talk from Tesla. It shows an example of such a near accident event which happens in front of the test vehicle, and which probably can be captured sporadically in the real world, but yeah, you probably cannot imagine recreating and reproducing this use case in order to capture training data. Okay. Yeah. So here I want to give a little bit of a feeling what current state of data simulation is. So there is a bunch of data sets which has been used in the community, in the research community in recent years. So one of the most, probably one of the most notable data sets which appeared almost 5 years ago was the data set called SYNTHIA. It had several thousands of samples of traffic scenes rendered in different conditions, in different light conditions, in different or daylight conditions, probably also weather, but with, I would say, limited realism. The next important milestone in dataset simulation was the dataset from Sebastian Richter and co. So this research group, they used the popular computer video game called GTA 5 to render more than 25,000 samples together with corresponding annotations. I guess they provided semantic segmentation and also recently the bounding boxes for those traffic scenes. And so they actually leveraged this the quality of rendering and the realism of existing video game. So there are also the simulated data set called VIRTUALKITTI. The goal of this data set was to create simulated one-to-one correspondences to existing samples coming from original dataset Kitty. So here on the slide, you can see in the first row, these are the original samples from Kitty dataset, and in the second row, you see the recreated simulated images in the first version of VIRTUALKITTI, which was released also several years ago, I guess 3 or 4 years. And last year, this research group released the second version of a VIRTUALKITTI dataset, and those samples from this dataset you can see in the lower row. So basically, for all dataset goes the same, that realism of created data is rather limited. Especially, you can see it especially in those samples where real traffic scenes are tried to be replicated. So from my point of view, one of the most realistic simulated data sets released in the last years was the data set called Synscapes from 7D Lab and University of I forgot already the name, but shouldn't be a problem. So So here are some samples from this Synthscape dataset. It's also large-scale data set, embracing more than several tens of thousands of samples in really, really good rendering quality. You can see it on this slide. There are also some players in the industry, or also in the research community, such as Parallel Domain, which do a lot of work in data simulation and in the research in the research area of perception using those simulated data. Yeah, so those were some of the state-of-the-art data sets in the community. But it's worth mentioning that despite of multiple advantages, generated data offer several challenges, and one of them are dedicated. So one of those disadvantages, it's the problem which most of the works in community are dedicated to, and it's called the covariate shift. And this issue is evident on this plot. What you can see on the slide is that the slide shows a detection model which has been trained on a set of data, data sets, and tested on 6 real and synthetic data sets. So to be more clear, I highlighted those the training results and performance results of this network. So here highlighted with dark green, those are the results of the detection network when it was trained on synthetic data and tested on synthetic data. In the light green, I highlighted the results of the same perception model, which has been trained on real data and tested on real data. So performance degrades slightly. But the most problematic ones are those highlighted with the red. And this is exactly where the model has been trained on synthetic data and tested on real data. So we take this perception network, and we train it, for instance, on playing for benchmark data set with 25,000 samples. It's colored with purple, and we test it, for instance, on BDD data set, or it's depicted with a star, or we test it on on the cityscapes, and which depicted with a cycle. So in all those results, it's quite evident that that performance of detection networks degrades. For instance, for several experiments where the network has been trained with Carla dataset and tested with BDD, the drop is really significant. So this phenomenon, which we attribute the performance degradation, commonly called the covariate shift. And so what is actually the covariate shift? If we take a look on the book of the authors, if we take a look on this on the data shift in machine learning book, so the putting definition of the book of the covariate shift in a more simple word, when the input distribution of machine learning algorithm changes, whereas conditional distribution of the output or predictions given the inputs remains unchanged, this is exactly where we observe the covariate shift. Just to illustrate this this setup, I'll show this slide with the so here's a good example of a setup on the covariate shift. The distribution of the prediction is basically staying the same, whereas the input of the input distribution changes. In simple words, when we have when input distributions are different. This is exactly where we have these set up under covariate shift, and it's not only applies not only for simulated and real data. We can see it in multiple examples. So, for instance, here's a setup under covariate shift with the data acquired at different locations. So, for instance, US on the left, Germany in the middle, and China on the right. So the same situation with the data acquired in different weather conditions: sunny, summer, sunny, snowy, rainy, anything you can imagine. Same thing applies to the data acquired in different light conditions, daylight images, and images acquired in the night. So it actually all falls in this category where we experience the covariate shift, or also domain shift between the data. Yeah, so researchers basically try to tackle this gap problem by means of domain adaptation methods, and they typically rely on generative networks which are based on adversarial training in order to translate those synthetic data into closer representation of the real data. And those methods, they actually achieve visually appealing results, but they commonly reveal the same problem of semantic inconsistency of such sim-to-real transfer. So CYCADA, which you can see on this slide, is probably one of the first and mostly acclaimed works in this direction. The CYCADA, I actually assume that most of the community is familiar with these generative networks paradigms, so I wouldn't go too much into details. So the CYCADA is—
Yes, they're familiar.
Okay, cool. So it employs two GAN networks to translate images from one domain, in this case synthetic, into another, in this case real, and it utilizes the cyclic consistency laws to enforce that content of the original input samples will be preserved. So basically what it happens, we learn those mapping functions so that if a input sample is mapped into target domain and back, the content of the image will be preserved. And this is the key idea. As I already mentioned, most of those approaches based on GAN framework suffer from same problem. They reveal semantic inconsistencies while sim-to-real translation, and there has been several, quite a lot actually, approaches which try to tackle this inconsistencies results. So most of them enforce some kind of constraint into the learning pipeline, so that it penalizes a network where translation is getting inconsistent. And in this case, for instance, a work called CYCADA, it's already dated 4 years back. They introduced so-called task laws, where a pre-trained segmentation network provided input for the for a learning objective, in a way that if segmentation predicted for source image and translated image does not match, that it implicitly shows that translation is getting sim-to-real translation is getting inconsistent, and in a way it will penalize then the whole objective and makes this translation more consistent. Yeah,
I think we have a question from Alex.
Oh, sure.
By the way, I didn't ask Artem, what is it okay to ask just at any time, or do you have question time specifically?
I guess it's okay to ask a question in the course of the talk. We just need to take care of the time so we don't get.
I will be monitoring the time. No worries.
Okay, cool.
We
Yeah,
have
Tom,
an hour
actually,
left.
yeah, I actually have a short question. Tell me if it will be too long. The question is, we are talking about sim-to-real in terms of trying to make a photorealism, right?
Yes. So
does it?
in
Yeah.
effect,
Okay. Could it be technically that photorealistic image? It's still simulated image, and it will fail on real data that you have, because the photorealism, I would say, can be photorealistic for the human eye, but it will be different for machine learning model, and it will look completely different because of some reputational pattern or something else that you can't easily catch by human eye.
Yeah, it's actually, yeah, this is the good point. And personally, I also don't like the term of realism much. First of all, I'm not quite sure how we formalize this realism in this case. So this is the first thing. And second thing, so if we take the best renderer we have at hand, even the one which has been used for Game of Thrones whatsoever, and try to render realistic imagery, then if it comes to a downstream task, for instance, if we want to use this trained network for predicting something in the real data, then we probably will still have this domain gap between sensor representation of our target data and this 100% realistic imagery. So so yes, in this case, it's rather it would be more correct to say in a simple words, visually similar to target data. And so GANs are actually quite good at it, and they can really generate data similar to what we use as a target data when we train a GAN network. Was another thing that I wanted to say, and yeah, so it's, and basically what GAN networks do is in simplified mathematics, we have the input distribution and we have target distribution, and we end up with some simulated distribution which is close to target data. So this is how we can formalize a little bit this visual similarity to the target data. But yeah, realism in this case, from my point of view, it's also not 100% accurate term. Yeah. Okay. I will continue then. So at this point, I would like to introduce one of our works where we try to enforce this semantically consistent sim-to-real domain adaptation. Yeah. So just one remark. I guess this topic is the sim-to-real domain adaptation and realism per se is realism of this adaptation is quite a hype topic now. So if we take a look on this video from Intel Lab and Ladlen Colton, the video which accompanied the paper they published recently, it got more than 3 million of views recently on YouTube, so which is quite a number for a video which accompanies a research paper. So it's quite a hype. So if it happens that students will watch this presentation and are interested in this topic, don't hesitate to contact me. We have a bunch of topics which yeah, might be interesting for you for a master thesis or bachelor thesis. Just short remark. Yeah. So what do we want actually to achieve with SYM-to-REAL domain adaptation, or with this work? So we want to expose our model to the real world via real data set, for example, cityscapes, and we want that this generative model picks the appearance of target data, which includes all the appearance characteristics which we as human can think about. It's, for instance, this surface textures or lane marking colors, any kind of visual stuff. So this example of this appearance learning you can see on the right picture, which I highlighted with the green squares. This is what we actually want to have. But we also want that this translation does not reveal any class confusion or inconsistencies while we apply the learned realistic style. Such inconsistencies I highlighted here with the red color, and they appear actually also due to this distribution shift that we have in underlying domains, or the data which represent underlying domains. There's another criterion which we like to enforce, is that we don't want to so we want to avoid integration of any components to constrain data generation, which would include pre-trained segmentation networks, or touching the rendering process, getting access to rendering artifacts like G-buffers, albedo, whatsoever. So we want to try to do it in strict mathematical defined ways. So we want the key idea of the method is that the method performs content disentanglement by employing shared content encoder and shared decoding, which operates on learned content features with fixed style codes. So what do I mean by that is, so we follow the assumption that synthetic and real data for urban traffic scenarios reveal common or domain agnostic features describing the content of the scene, such as cars, objects in the scene, pedestrians, whatsoever, and domain-specific features describing the performance, such as textures, colors, and so on. We employ a single network to encode the common features of different domains with randomly sampled style codes for each domain to represent the domain-specific features. Given an extracted content feature vector, it comes here on the slide after the last rest block, and a sampled style vector for one of the domains, our single decoder can synthesize an image in the particular domain. And this is how we learn our encoder-decoder architecture. And to generate the images in cross-domain setup, the encoder embeds images from the source domain into content code, then normalizes the content code with the target domain style code via adaptive instance normalization, and this is how it creates the cross-domain transfer. So in our approach, the pipeline basically looks like this. It has a shared content encoder E and a shared decoder G. So we also have two domain discriminators, which are implicitly mentioned here by L adversarial. And as shown on this scheme, the encoder embeds the input sample XA or XB into a latent code CA or CB. So we enforced, during the training, we enforced the C to represent common features between two domains. Hence, we call it content. So they are not so content. It's in the matter it's our human understanding. and in this part, C it's not the content yet, but through the losses we apply in the training and this training process, we want our encoder to disentangle the code components, so kind of filter them out. And the decoder G receives the code C together with one of the predefined domain-specific codes, SA or SD, just in order to distinguish between two domains. So we enforce two constraints in order to achieve the disentanglement. The first one is intra-domain reconstruction. The sample XAA will be generated from the CA and style SA, and it must be equivalent to the input sample XA. And the same goes for generated sample XBB and input sample XB. And we ensure that those XA equals XAA and XB equals XBB through just plain reconstruction laws. So the second constraint is the inter-domain reconstruction or cross-domain, and we want to ensure that XABA, which is generated from CAB with the style code SA, coming from SAB, shall be equivalent to the sample XA. And this is where we also have this cyclic reconstruction laws, which basically should take care that XBAB is equivalent to XB. And lastly, we apply adversarial laws on the cross-domain images to match the distributions. So to train our pipeline in accordance to those intra-domain and cross-domain constraints, we formulate our laws as follows. So it basically consists of two intra-domain reconstruction losses, LAA and LBB, two cross-domain reconstructions, LABA and LBAB, and two adversarial losses. And yeah, reconstruction losses that I described previously are quite simple. Encoder E is applied, for instance, for one direction, encoder is applied on an input sample XA, generates content CA, which is then taken as an input for a generator together with style code SA, and this is how we get the XAA output sample and compare it to XA. So pretty standard. Yeah. So here I would like to show the results of our translation method. For the experiments we use to a large-scale data set for urban traffic scenes, the real is the cityscapes data set, and synthetic is the playing for benchmarks data set, the one taken from video game GTA 5. And yeah, the results of the transfer of this transfer is on the slide. Every odd line contains synthetic input image, and every even line contains the corresponding generated output. So it actually demonstrates quite a good quality of translation, and this can be observed especially on those on the patches of road surface, for instance, or also yeah, the lane marking colors, which are getting changed. We also compare our method to state-of-the-art domain adaptation method. So I picked only the ones which are doing domain adaptation in the unsupervised setup. So in a setup where we don't have one-to-one correspondences between synthetic and real data. Yeah, for the network called MUnit, we disabled the component, the segmentation network, so that we put all state-of-the-art methods in a similar conditions where no so to remove this kind of bootstrapping by taking additional networks into pipeline, additional pre-trained networks into pipeline. And yeah, so our method shows quite a good consistency for all classes while the translation, and especially you can see it for the classes such as vegetation, sky, road, and also the ego car, which is also a good highlight in comparison to other methods. Our method keeps the ego car not changed to this to the typical ego car coming from the target dataset. Yeah, so we also
are these cherry-picked examples?
They actually they are not cherry-picked examples. So this the mismatch, the content mismatches, they're quite typical for the existing networks. So if you take this CYCADA approach and just plainly train it on GTA and CYCADA, you will see this inconsistency almost in every single sample, which is actually not the case for ours for our data generation pipeline. But the code is actually public, so yeah, you can take a peek and you can try to train it, and you'll see that basically those results are not cherry-picked. Yeah. So there's
Nice.
another point.
Another question.
Mm-hmm. Sure.
And maybe it'll come later, but training times, hardware, how many images or video pieces were generated? How long did it take, and on what hardware?
Mm-hmm.
Not generated, trained is more the right word.
Yeah, exactly. So we have a bunch of experiments, and just in different hardware, but just to be sure that the numbers add up. So the last training I've done was P600 NVIDIA P6000 with reduced resolution. It was just 512 by 256. 3K 30K GTA dataset and 3K Cityscape dataset, and it was ready over the night, basically. And P6000 has, I guess, 24 gigabytes. So it's really lightweight network, as I mentioned. As I mentioned before, it has only one encoder and one decoder together with two discriminators, but still, and the architecture of encoder decoder is pretty straightforward. So in this case, I guess it's the same what the M unit is using. Actually one-to-one already, almost. And yeah, so it's just one encoder, one decoder. It's really lightweight. Yeah, I will just put the link to the code, and you don't need really any fancy Tesla graphic cards to train this. It can go on pretty simple P6000 network over a couple of days. Higher resolution, of course, makes things more complicated, but to see the initial results, you don't need more than 1 day. Yeah. Just to get back on this content disentanglement content, we want somehow to verify if this content disentanglement actually happens. So we use the TSNE method to visualize the content vectors. So what we do, we take the encoder, which has been trained in our setup for 200 epochs, and we apply the TSNE algorithm on to the generated content vectors. The TSNE, probably everybody is familiar with TSNE. It does some kind of dimensionality reduction, takes multidimensional input vectors and generates those 2D vectors, so we can put it and visualize with 2D image tools. So I hope you see that we actually have 4 kinds of markers on this on the left. It's the red cross, red square, blue cross, and blue square. Red cross is the input sample from one domain, the XA, and the red square is the cross-domain transferred image, cross-domain transferred content, which is basically CABA. So we compare red crosses XA, the CAs, with cross-domain transferred content vectors CABA. Those in red. And the same in blue, we have the input content vectors CBs and the cross-domain transferred content vectors CBABs as a blue squares. And although we have not a single constraint on the content, so we don't apply any losses on constant content, nothing. The encoder learns that input content vectors should be identical with cross-domain transferred content vectors. We also perform some kind of
nice.
Yeah. We also perform.
Gives a lot of confidence in the method.
Yeah, so for me, it's actually a kind of confirmation that that the encoder understands on the content the same thing as I, as a human, understands on the content. So it doesn't matter if we apply those visual appearance features into the output samples. For the encoder, content stays the same. We'll try to evaluate the method also in quantitative terms. We don't apply any statistical distance measures on the outputs. So for us, it's more interesting. We say we do good sim-to-real adaptation if our data used for the downstream task performs well. So what we do is we train domains with semantic segmentation network. In this case, it was DRN. We trained the DRN on different transferred images, and we always evaluate it on Cityscape's eval subset. So the first line is DRN trained on Cityscapes and evaluated on Cityscapes, and it's still kind of the oracle and the upper bound for all those methods. Then in the second line, you see the same approach trained on pure synthetic GTA data, playing for data dataset, and also evaluated in Cityscapes. And this is exactly where you see, for instance, on the mean IOU score, the significant performance drop, and then different state-of-the-art adaptation methods and DRN trained on the outputs of those networks. So we achieve quite good performance in accuracy terms and in the mean OUU. We also improve the method. Our method improves the performance on several classes, especially, for instance, the typically mismatched classes in a setup, GTA cityscapes for vegetation, for instance. So we can improve it more than by 5%, yeah, compared to the other methods. Yeah, so that's actually that's all I wanted to tell regarding the semantically consistent synthetic-to-real domain adaptation. And before I switch to another work I wanted to present, okay, since we have questions during the talk, we can actually you can state the question whenever you want.
I have a short question as well. So did you evaluate if domain training on data generated with domain randomization would work better or worse rather than data generated on domain adaptation? So basically, domain randomization, when you have very simulated data, it looks like simulated, but you have the with randomized domain. Yeah.
Yeah, actually, I'm not familiar with any recent methods. So I guess the last one, domain randomization approach used in this setup. Using this setup was from NVIDIA, a research group, several years ago, but since then I haven't seen much of the progress on that. And I guess back then the results were comparable with state-of-the-art methods of this time. So, for instance, CYCADA, or they also compared the data, the results in a similar manner of the on the downstream task as we do. And it was comparable, but now I cannot answer your question for sure, because I haven't really followed this direction of domain randomization, and nothing came across my my literature research recently which would kind of stand out. So now I actually would say that probably the domain adaptation would surpass the domain randomization approaches.
Thank you.
Just a gut feeling. Yeah. Okay. So now I would switch to the next work we presented this year, and this work has taken slightly different direction. Maybe even orthogonal to the one to the typical sim-to-real adaptation, where you have simulated image as an input and realistic image as an output. So in this approach, we also have the key concept is the content and style disentanglement. We say that content is something which is domain agnostic, which is similar for input domain and output domain, and in Empirics, it's what makes the difference. So in all examples, there's always one thing, especially for traffic scenes. We also have the roads, we also have the sidewalks, cars, whatsoever, and this is actually make the content for us. And in this work, we want to find the suitable descriptor for this content representation, which is actually the more explicit representation, which we also can interpret as a human. And one option to So one option was this implicit content learning, which I presented in the previous work, in the form of latent vectors. But if we want to have flexibility and we want to be able to manipulate the content of our traffic scene, we would need the explicit representation of the content of the traffic scene. And in this case, we use the scene graph concept. Scene graph is basically an abstract data structure used for describing scenes by encoding objects as nodes and relations between objects as edges, so that the whole scene can be the traffic scene can be represented as a directed graph. And by using this scene graph, we allow our model to reason explicitly about the objects in the scene and their relations. The concept of scene graphs, I guess, was used in the work of the Justin Johnson in the paper of image generation from scene graphs, and it used to be an alternative to a textual scene description, also used for image generation, and showed several advantages in comparison to textual scene description. Another important concept needed to be introduced is a graph convolutional network. And a graph convolutional network is a network that operates obviously on graphs. So given a graph G with vertices V and edges E, such a GCN takes as input a n by f feature matrix X, where n is a number of nodes and f is a number of input features per node. And this input features could be anything, such as, so you can use the size or color. It's really like flexible concept. So it also takes a second matrix, the n by n matrix, which represents the graph structure in form of adjacency matrix A here. So actually every simple graph convolutional network and its layers can be represented with those two formulas actually.
I just sent a link here. We had 2-3 months ago a talk exactly about this topic, convolutional graph neural networks. So anybody who's interested can dive deeper there.
Yeah. Cool. Yeah. So our method in this regard also resides on the concept of graph convolutions. It focuses on unsupervised traffic scene generation from those synthetic scene graphs, and we actually don't have the pairs of synthetic and real scenes, so they're just not available. So we derive the synthetic scene graph from procedurally generated 3D scenes that does not provide visual characteristics such as textures or materials. So for synthesized scene graph, we then produce an image of corresponding traffic scenes, which should resemble the content of the underlying synthetic scenes and the realistic appearance of the target data. And again, we have our pipeline, which consists of several parts. Those are the simulation. Yeah, actually, just
Yeah.
Was it a question? Because I'm not sure I can hear well.
No, you were saying actually something, and then.
Okay, yeah. Sorry, I just heard some voices in the background. So, so I had another picture before just to visualize our starting point. So we have this 3D scene, which is actually procedurally generated 3D 3D representation of city streets, and it lacks textures, materials, any visual components which we typically see in rendered images, just yeah, to visualize it better. And so our three components of the pipeline is this actual procedural simulation, the synthetic scene graph processor, P, and image generator G. So simulator provides synthetic scene graphs and the layouts. P is a graph network constructed of graph convolutional layers. Yeah, so P is a network constructed of graph convolutional layers in the encoder and plain MLP-based decoder, so nothing fancy. The encoder extracts features from the scene graphs and encodes per object layout embeddings. The decoder turns the embeddings into layouts. So we train the the scene graph processor P by the guidance of LSG on this picture, which is basically the L2 distance on masks MI and bounding boxes BI, plus the adversarial loss. Then when we have those scene layouts, we they are used as an input for image generator, which is basically a 2D fully convolutional encoder decoder architecture network trained in unsupervised way using adversarial and noise contrastive laws to be able to synthesize the images X. So this is the rough overview of the pipeline, and to enable this unsupervised learning procedure, we apply both adversarial and noise contrastive losses for the training. Yeah, so our final loss objective consists of two terms: the loss on scene graphs and loss on generated traffic scenes. The loss on scene graphs is a sum of L2 losses on bounding boxes and masks of particular objects, plus adversarial loss on masks, and loss on traffic scenes is just adversarial loss plus noise contrastive part. And actually the noise contrastive part does all the tricks with the tiny visual features which are generated by the pipeline, and which I will show later in the results slides. So what we get in the end, we train this pipeline with in our standard setup with the so originally the pipeline is dedicated to procedurally generate procedural simulation with no features, but we also, for evaluation purposes, we also can use it with standard synthetic data sets, like playing for benchmarks, because all we need from the simulation is the bounding boxes and the masks of the objects. That's actually it. in this context, in this context, for our experiments, we use playing for benchmarks as simulation, cityscapes as the target data set, plus SYNScapes data set as simulation, and Berkeley Deep Dive. So on this slide, I'm showing the images synthesized from synthetic scene graphs obtained from playing for benchmark data set, and appearance learned from the cityscapes data set. Here, basically the same. We use SYNScapes data set to derive those scene graphs, and the images generated by the by our pipeline represent the visual characteristics of the Berkeley Deep Dive data set. Yeah. So what we also can do with this pipeline is we actually can take one arbitrary scene graph from any simulation, from GTA, from SYNScapes, or any in-house simulation, and produce images in the optics of any target data we wish. So second row here shows the traffic scenes generated in DDD looks, and the lower row images show the same traffic scenes is seen in the looks of cityscapes. But actually, if we have so what we need is just to drive around, gather the data. It can be also a sensor of any configuration. It could be your in-house sensor, and you drive around and have this corpora of data. No need for ground truth annotation whatsoever, and you're ready to go and can generate images. Yeah, so this is basically the same. We take one synthetic scene graph and produce several traffic scene images in two styles, DD and cityscapes. Yeah, what we also can do is that additionally to the objects existing in the traffic scene, such cars and bus, we also introduce, just in order to make this whole pipeline work in our setup, we introduce multiple classes which are characteristic and typical for traffic scene scenarios, such as a road, sidewalk, vegetation, and building. So this so that we can have the whole palette of information describing the traffic scene. And just to verify this, introducing those classes is effective, we perform several experiments with manipulating those classes in the traffic scenes. So what happens here is we started with some original with some scene graph, and we generate a corresponding image for this scene graph. Next thing, we changed the class for some particular object. In this case, this the tree object. We change it with we pick this building object on the right and swap it with the tree or vegetation object. And what happens in generated traffic scene is that the object which corresponded to the building object will be replaced by vegetation. What we also can do is that we can manipulate the relations between the objects in the scene. So now instead of tree right to the car, we change the relation to above. And in the step 3, the car which is located in the scene appears under the object which corresponds to the vegetation. As the next thing, we can also swap back, revert the class back to the building, and we see that this building patch is coming back as in the original image. We also, since we use the synthetic scene as the starting point of data generation, we have all the spatial information about this scene. because actually in our render we have everything. We have all the 3D information we have. And what we can do, we can also encode those 3D parameters and spatial attributes into the scene graph, and then we are able to manipulate the traffic scene generation with respect to spatial attributes. So here, for instance, here's the on the left side, you see the traffic scene without the car in it. Then we put a car with some particular spatial attribute set to 5, for instance. It appears on the left side on certain distance to the ego car, and then we change the spatial component z to some lesser value, and the car is dragged along the z-axis towards the ego car. Yeah. So what else can we do with those spatial components? We can encode the spatial relations, since we know where each object is located in the synthetic 3D scene. We can also encode spatial relations between those objects, such as in front of or behind. So here I would like to, in this slide, I would like to show how this manipulation can happen. So we start with some scene graph and generate some arbitrary synthetic scene graph and generate a traffic scene for it. And then we introduce, so we have 2 cars currently, although they are quite messy, I should admit. I hope that they're also distinguishable for you in the image, those 2 cars.
We can see the difference for sure.
Okay, great. What we can do is we can introduce the spatial relation between those 2 cars, for instance, in front of. And on the second step, we see that the right car appears, at least for me, kind of closer to ego car than the left car. When we swap this spatial relation from in front of to behind, then we see that the right car goes into the, say, background or relative to the left car behind it. Yeah. Let me see. Oh, that's actually it. That's all what I wanted to tell you about this method. Maybe now I still have some time to show how it works live, because I have this nice demo which corresponds to this method.
In the meantime, everybody, think about, if you have a question, you want to write it down, take this time, write it down, or think about it in your head. Because we'll have the question part coming up really soon.
Okay. I'm starting it now. Okay, now I need to change the sharing the screen. Okay. You must be seeing my screen, my browser now, with the gray screen. Peter, can you confirm that?
Yes, we see.
Okay. So this is a example for this for such traffic scene generation with those scene graphs. So now I want to put like first object, the road, into the traffic scene and generate an image. So no, move this one. So this image looks pretty creepy. I should admit, probably because it's just not enough data to generate a reasonable traffic scene with this. So now I put the sky above the road. Probably still a little bit messy, but less than that. And we can already distinguish several objects in the scene. So the one corresponding to the sky and the one corresponding to the road. And the more data we put and the more constraints we put in the scene, the better it gets. So I have some predefined scene graphs in this live demo. So this is the one I presented before, and so we have the traffic scene with the car object on the left side, and yeah, don't judge me for my web design and web programming skills. And so what I want to do now.
This is a super cool thing, by the way, no judgment.
Okay.
This is super cool. I would recommend if you have something like that is like a video or an image of this, post it on our subreddit along with the link.
Okay,
I am sure people want to play with it. I'll put it in the newsletter. And
Sure.
Extremely cool thing. If you can play with any neural net, it's always a big plus. So
thank you.
Nice.
I'll do that. Yeah, so I just want to demonstrate this manipulation use case, which I showed before on the slide. So we have the car and those 1, 2, 3, 4, 5 corresponding to the distance to the ego car, or depth, basically depth in the traffic scene. So now we define it. Now we set it to 1, and the car generated with the traffic with our method should appear closer to the ego car. We set the 5 back, and it should be pushed further into the depth of the traffic of this generated scene. Then again, we can push it back. Another thing, what I've done for it's just like I this car. I delete the car, generate the traffic scene again, and the car is gone. So this is how this traffic scene manipulation works.
Can I have a short question? Sorry. Can you guarantee that the car is gone? Because when you generated the first image sky above the road, there were already some objects. There were no cars, but there were some objects that you did not ask for, but they appeared.
Yeah. So in this particular approach, which we're doing, we don't set this goal for like consistency, and so actually, answering your question, I actually cannot guarantee. And of course, since it's trained in unsupervised way and using the adversarial networks, it can, let's say, hallucinate objects, right? And this is actually what happens in what happened in the case with those 2 cars I showed before. The generated objects are still quite messy, and I would mostly attribute the issue to this to the fact that the network just starts with this abstract description, car left to another car, and so on. Yes, back to your question, no guarantee. It definitely can hallucinate some stuff, but the more constraint you put in your scene graph, the more bounded is the network in terms for the generation. So what we focus actually here is just to have this. This is one of the reasons why we are not really comparing this approach to any state-of-the-art methods, because yeah, there is not much to compare with, and so we wanted to have this approach where we can manipulate the generated traffic, the generated image and the generated scene. But yeah, there is still plenty of stuff which can be done in terms of quality and image generation quality, and also yeah, certainty what's generated. it's a good point. It's actually the valid point for any yeah, simulated data. Yeah. Yeah, that's all.
Anyone else? Any other questions? I feel like we can wrap this up, Artem. So if you have any closing remarks, go ahead, and then I will finish up.
No, that's actually that's it. Thanks for your attention. And if there are coming up questions following after the talk, just don't hesitate. Peter showed me the Reddit channel or the Reddit thread, and you can also contact me by email. Whatever works for you, I'll be happy to hear back.
So I just posted all the places again where you can find the community. The subreddit is also in the chat here. Artem, if you're interested, you can also join our Discord server. Sometimes people are asking questions there in this field, and if you feel like this is something that you want to contribute, feel free. Some people do, and it's quite nice communication going there. Everybody who stayed, thank you for being here. I'm sure people will be watching the recording much more. So for those of you who have watched the full thing, we're always glad to have the audience here. The more engagement we have, the more we know it's relevant for you guys. And so thank you for being here and showing us. Oh, we have from Alex. Special kudos. Thank you. Thank you. Hard work, but it's okay. It's fun. Artem, thank you for joining today and showing us. I love the demo. I think I'll play with it later on. Thank you for sharing your research. And it's nice that it is straightforward and simple, yet very useful. This is a good combo. So good job on this front.
Thank you, Peter.
If there are no more comments, I think we will close for today. Everybody, wherever you are, have a good day, have a good evening. And I think I'll see you next week.
Bye-bye.
Bye for now.